This video is about similar polygons, and it's found in your text in section 7-3. What do we mean when we use the word similar in ordinary everyday speech? This boy's hair is similar to Ramen. These two girls are very similar. Well, in math, the meaning of the word similar, when used next to the word polygon, is very specific. We have a definition of similar polygons, which says that, first of all corresponding angles are congruent. All corresponding angles are congruent. Okay, so if we were to label this vertex A, it would correspond to vertex A prime. The one with two congruency marks, let's call that B, that would correspond to vertex B prime, and so on. And these angles all have to line up with each other, just like when we were discussing congruency between polygons. But here we have similarity, not congruency. And the difference is that the corresponding sides are not congruent to each other. Instead, they are in proportion to each other. So the side that's in between A and A prime, A and B, has to correspond to the side that's between A prime and B prime. These two sides correspond to each other. And we write the fact that they're in proportion as a ratio. So side AB, the ratio of side AB to side A prime B prime is 2/4, or the same as 1/2. And we can check, let's check one other side just to make sure that we're on the right track here. Suppose we called this vertex C and this vertex C prime. We could see that the 3-meter side in this polygon corresponds to the 6-meter side in this polygon. Okay, so BC to B prime C prime, the ratio there is 3:6, which is also 1/2. So the side lengths have the same ratio. And if we wanted to figure that out for all 4 sides, we would find that since these two polygons are similar, the ratio between this side and this side to this side, would also be 1/2. Every side would have the same proportion. Symbolically, when we speak about similarity, we use this symbol. Looks kind of like a congruency symbol, except it only has one squiggle, and that is the symbol for similar. So if we write quadrilateral ABCD is similar to quadrilateral EFGH, this is how we would write that statement. So which two triangles in this picture do you think are similar? Well, we can't use a protractor to measure all the angles on the screen, but suppose I were to mark some congruencies here. Suppose I were to mark this and this angle, this and this angle, and I were to tell you that all 3 of these triangles are right triangles. You might start to suspect that triangles A and B are similar since all of their vertices have congruent angles. Triangle C looks a little bit more narrow or squashed than triangles A and B, and that's, although we can't trust our eyes and we would have to measure with a protractor, we would probably find that angle C was not congruent to angles A, to the angles in triangles A and B. And in fact, this shape would not be similar to triangle A. But this shape would be similar if we were to measure these 3 angles and found that they were all congruent. Then we could look at the sides, and we have this side which is 4 units long. This side is 2 units long. Okay, let's go over here. The corresponding side on triangle A is 2 units long to this corresponding side, which is 1 unit long. So notice that the proportion of 4 to 2 is the same as the proportion of 2 to 1. So in fact, these two triangles do turn out to be similar, and we can prove things like that when we get a little further down the road and start using trigonometry. Okay, here's a new word for you, scale factor. This sounds like the term that we use for scaling things up and down. And in fact, it's very much related to that concept because triangle B is clearly a scaled down version of triangle A here. And that's why we talk about having a scale factor of A to B. So the scale factor of A to B, let's just remind ourselves, in this case, A is the big and B is the small. So a scale factor of the big shape to the small shape has to be something less than 1 because we're shrinking triangle A down to be the size of triangle B. So again, let's look at the sides that correspond to each other. This side length was 4 and this side length is 2. If I want to shrink triangle A down and get it to be the size of triangle B, I have to take this side of length 4 and shrink it down to become a side of length 2. So the scale factor in this case would be 2 over 4, or 1/2. So notice that the 2 came from triangle B and the 4 came from triangle A. 2 came from B and the 4 came from A. If you start to get confused about which number to put in the numerator and which number to put in the denominator, just ask yourself, am I going from big to small or small to big? Since in this case I'm going from big to small, I need something that's less than 1. It should be a fraction that's less than 1 because I'm making the shape smaller. Let's do an example problem. We're told that quadrilateral TUNE, or TUNE, is similar to quadrilateral T prime U prime N prime E prime. We're told that. We don't have to prove that these two quadrilaterals are similar. And we're also given the vertices that correspond to each other. Just like when we were working with congruent triangles, when we're working with similarity, we're told by the way that this statement is written that vertex T corresponds to vertex T prime, so that this angle here, being 135, would tell us that angle T prime is 135 degrees. And so the same as when we were talking about congruent triangles, we're told information about which side corresponds to which side. So side TU corresponds to side T prime U prime because those two letters are written first when we named the quadrilaterals. So TU corresponds to T prime U prime. We don't know what that is, but we know that that's the side that would correspond to side TU.